just a quick look at the agenda for today's webinar. We have three main points, three main sections here. We have the first one dealing with the selection criteria. So it's a quick guide how to make the right choice of accelerometer for your application. Then I want to give you an overview of the key requirements for automotive applications. We'll have a look at the main applications, excluding crash at this time for automotive, although we also have products in that area. I will match the applications with the Kistler products, so with the Kistler accelerometers, so that you have an idea of the type of products you can use for such conditions. And then finally, I included a sort of small bonus section, practical considerations. I really want to give you suggestions how to make the most out of your test with some really basic consideration you can make when setting up your measurement setup. So let's get this started. Let's start with the selection criteria. And let's start with a short overview of the anatomy of a sensor, of an accelerometer, actually. So an accelerometer is a sensor which is basically attached to the surface of which you want to measure the vibration. So vibration travels through it, it reaches a post to which a sensing element is attached to, and which in turn is attached to a seismic mass. And basically, because of the mechanical vibration, the inertia and the stiffness will make the sensing element go through a stress, and therefore these sensing elements, because of the material it consists of, will produce an electric charge. This electric charge will be measured, but here the whole point is that we are moving from a mechanical input to an electrical quantity. And now the goal, your goal, and also our goal as a sensor manufacturer, is to make sure we control the relationship between the input vibration, the input mechanical vibration, and the electrical output. And now, of course, there are design elements that make sure that this relationship is consistent, but there are also some parameters which react to external influences, because of course, in most of the cases, these sensors are put into conditions which would be aggressive. For example, I can think about an engine bay, for example, or maybe you have electromagnetic fields around. You might have dynamically, so temperatures which would change over time. So all these elements will try to perturb the relationship between the input vibration and the output signal. And the best way to have an understanding of how these elements are impacting this relation is actually to have a look at the data sheet. The data sheet is where you will find all this information, all information related to your sensor, but is also the element which allow you to make the choice for the right sensor. And now on the data sheet, you're going to find a lot of parameters, many of them. And my goal here is to guide you through the key ones that allow you to make most of the choice, let's say 95% of the choice. And now, if this is a starting point, I would say that first thing you need to consider is the type of technology you might want to adopt. Now, when it comes to technology, here we have three different types, which are the main ones we sell as Kistler products and also available on the market more in general. We have, first of all, charge sensors, so charge piezoelectric sensors, and they work in pretty much the same fashion I described. So you have a vibration that enters the sensor and puts into vibrations, first a sensing element and then a seismic mass. And these sensing elements, because it's made out of quartz, ceramic material, or even a piezo star, which is a proprietary Kistler technology, it will get out a charge, an electrical charge out of such a stress condition. Such a charge is going to be taken out of the sensor and transformed into a voltage signal thanks to a charge amplifier. Now, this transformation happens outside the sensor itself. So the sensor itself does not have any electronics in there. And this means that the sensor as such can go usually to a rather higher temperature than the version with integrated electronics. We will see this in a minute. So usually you can reach higher temperatures with a standard charge piezoelectric sensor. However, for example, the cables that will bring your charge, electrical charge, to the amplifier will not allow a very large length. So you will not be able to use a very long cables with such a technology. Another advantage of this technology is the fact that you might have the possibility to control the electronics from the outside of the sensor. So you will have more flexibility in that sense. So you will be able to adjust the constant, the time constant of your sensor and the full scale of the output. Now, what I just said is basically that we have electronics which is outside of the sensor. So the natural next step is to bring electronics inside the sensor. And this is how we end up with the voltage IEPE sensor, so integrated electronic piezoelectric sensors. Here, as you can see in the picture, we have electronics mounted within the case of the accelerometer. So basically, the transformation from charge to voltage happens inside the sensor itself, and what gets out is a voltage. However, these sensors need to be powered, so you need to provide some sort of power to the sensor. A good thing of this type of sensors is that you can use longer cables. So it is common in the automotive to find 5-10 meters cables. This is reasonable. These are reasonable length to find in any almost nearly any applications, let's say, for automotive. A disadvantage that you might have with such a construction is that because you have electronics inside the case, you will not be able to reach the same high temperatures you can with charged piezoelectric sensors. Because of course, usually when you go above 160, 180 degrees C, you will end up with damaging the electronics. So it might be that your response at first is not going to be valid anymore, and then going higher, you might seriously damage the electronics and the sensor itself. An advantage, however, of this construction is that you can also store information regarding the sensor within the electronics itself. So you basically have the so-called TEDs, which will allow you to keep in there the sensitivity. And if you have 50, 100 sensors for your test, so a lot of them, and you want to import with the click of your mouse all the sensitivities for these sensors, you can easily do that with TEDs. When otherwise, without TEDs, you would have to do this manually one by one. So it's let's say it's a strong boost in terms of efficiency having the TEDs. These, however, I would say that the IEPE sensors with integrated electronics, are by far the most used accelerometers type in the automotive industry, I would say. And then we have the third type of technology, which is MEMS capacitive sensors. Now, these work with a little bit of different principle. We have an accelerometer, which again is mounted on the surface of which we want to measure the vibration. They will put in motion through a spring an inertial mass. Such an inertial mass is moving into a sort of small cavity. And thanks to the measurement of the variation of the capacitance of this small cavity, you will be able to measure the vibration of the object you're interested in measuring. So the working principle is different from that, and it has some advantages. So the first advantage is that you can go lower in frequency, down to 0 Hertz, which is, as we will see later, useful in many instances. Then we have that the cavity is actually filled with a gas, which is providing a critical damping. Therefore, the frequency response of this type of sensor is pretty linear, is pretty smooth. And this is a good thing. It provides really optimal frequency response to this sensor. And then we have a feature which is given by the construction. So basically, this inertial mass is mechanically bounded by the cavity around it. So actually physically bounded. So you cannot penetrate the cavity with the inertial mass. And therefore, this provides with a higher ruggedness to this sensor type, so to this construction. So having said that, we went through the key technologies that could be of interest for you when it comes to automotive applications. Then the next thing you want to consider is measuring range. So the measuring range tells you a little bit the maximum acceleration level you might reach during the test. Sometimes this is known because maybe you have past experience. Sometimes this is unknown because it's a new test for you. There you'd better be conservative. And here on the right-hand side, I provide you with a table just to orientate a little bit what type of G ranges you should use when it comes to certain applications. We will have a closer look at this later on, by the way. Then when it comes to the sensitivity, this is connecting two different physical quantities. So it is connecting a mechanical, let's call it mechanical, more mechanical quantity, the acceleration, to the electrical output, so input over output, which could be millivolt over G or picocoulomb over G, depending whether you're using a voltage sensor or a charge sensor. Here, it is common in many instances to look at the sensitivity, but because it provides an information which is a little bit less intuitive and more, it looks at things more from an engineering perspective, this is not always used. It is very often used the measuring range instead. So very often measuring range is providing you with, let's say, it has a higher priority in terms of choosing a criterion. There is also another parameter that might be worth looking at, which is the threshold. The threshold basically tells you the minimum amount of vibration you can measure. This is usually in milli-G. And this, I must tell you that it is seldom the case that you're going to choose an accelerometer because of its threshold. It is, of course, important to look at the minimum amount of vibration you can measure, but in automotive, you generally have rather high vibration levels, which are comparing them to the threshold. So only in the case you end up into micro vibration, you might want really to dig into the details and make a choice which is based on the threshold. This is just based on experience, let's say. However, it is a very important parameter you need to consider during your choice. A parameter which is gaining importance more and more nowadays with electric mobility is definitely frequency response. What this parameter is telling you is the usable frequency range over which your sensor is going to provide a rather linear response. This value is usually provided in between bounds, for example, plus minus 5%, plus minus 10%, or maybe plus minus 3 dB. On most of our data sheets, you will find both plus minus 5% and 10%, which are basically indicating you the type of frequency, usable frequency range, as you can see in the picture, over which the linear region of the transmissibility curve is within the plus minus 5% region, or 10 plus minus 10%. For example, here we have our 8763 B250 is one of our sensors, and this we will see it a little bit into the details later. At plus minus 5%, it offers a usable frequency range between 1 Hertz and 10,000 Hertz. And of course, if we would increase the range to 10%, it also increases the usable frequency range to 0.7 till 15 kilohertz. So it's a wider frequency range. That's very much depends on the type of application you want to deal with. We have also another important characteristic to look at for automotive testing, which is the thermal performance of your sensor. If you think about engine applications, for example, this is something we can't compromise on. And here there are two main items. First of all, we have operating temperature range, and this is basically telling you what is the temperature range over which your sensor is going to preserve the integrity. So this is specifying, usually for automotive, it is important to look at the maximum temperature within which you can use your sensor without damaging it. And then we have a temperature coefficient of sensitivity, which is basically telling you how the sensitivity is changing when you're changing the testing temperature. So when the temperature in the environment you're measuring is actually changing. And this is very important to look at, and I will show you now why. So let me introduce you the ceramic element. So ceramic sensing element is very common, probably the most used sensing element on the market. And now, usually these sensors, accelerometers, which use a ceramic sensing element, have a typical temperature range which goes around 120 degrees. Still, ceramic elements are very good because they are light, they have a very good sensitivity, so you can miniaturize the sensor. You can get a very, very small sensor out of it. However, if you look at the picture on the top right, what you're going to see is that the sensitivity to the temperature variation rather strong. So if during testing the temperature is changing somehow, your measurement, your accuracy will be impacted by that. A way to reduce such an impact is to use quartz elements. So if we go back to our table, you would use a quartz sensing element. The typical temperature range would be extended, so you would be able to reach higher temperatures. However, because of the limited sensitivity of these sensing elements, you will not be able to miniaturize to find very small sensors with quartz. And if we look at the level of thermal stability, you see that this behaves better than the ceramic elements. So all in all, quartz has a better thermal performance, but you still lacks of possibility for miniaturization. And because of these limitations, a few decades ago, Kistler has decided to invest in the development of a new crystal. And this is a proprietary crystal of Kistler, developed and basically grown in our laboratories. It's called PiezoStar. The PiezoStar crystal allows you to cover the same temperature range of a quartz. So it allows you to get to the maximum limit in general, in this case for IEP of a quartz sensing element. So it provides no boundary in that direction, but it allows you to have a thermal stability which is nearly perfect. So it's topping the market in terms of thermal stability, and the advantage you would get is that you don't have to correct your measurement. So if you would have a quartz element, you would have to correct the measurement if you increase the temperature significantly. With PiezoStar, you don't have to do that. Plus, because the PiezoStar crystal is more sensitive than quartz, you actually can have a smaller sensor. So miniaturization is again possible, and you can have a sensor which has the same dimension of a ceramic sensor. So we will see this in a minute. But the message I want to deliver with this slide is that when it comes to temperature, operating temperature range, and coefficient of sensitivity to the temperature are important factors, and have a look always at the sensing element you are considering for your selection, because it will have impact on the performance, on the thermal performance. Then we move to mass and size. Of course, size is important when it comes to space availability, how to mount the sensor, where to mount the sensor. This is important, but mass, it is important because it will affect your measurement. This is inevitable. Whenever you're measuring with an accelerometer attached on a component, you're somehow altering its dynamic behavior. This is physics. However, if the sensor is much smaller than the object you're measuring, such a change in the dynamic behavior of the measured object is almost negligible. It is important, though, that you choose a sensor with a mass which is much lower than the mass of the object you want to measure. Otherwise, what you will see is that the dynamics of the object is moving towards lower frequencies and lower amplitudes of vibration. So, when it comes to mass, always take into account the mass of the object you are measuring. It is important to consider the mounting method too, because you would have to mount the sensor to the measured object, and the way you mount it will influence the stiffness of the connection, the damping of the connection, and the mass of the connection, of course, and this will have impact on the accuracy of your measurement. Here, bottom left, I reported different mounting methods with increasing stiffness of connection. So we start with magnetic base, which compared on the right-hand side figure, you see that it offers the lowest stiffness. And then you can use, for example, adhesive mounting with a base, with a mounting pad, or without the pad. And this goes with increasing stiffness, or the best in terms of stiffness, of connecting stiffness, you might want to have a stud. So basically screwing the sensor either directly on the surface or with a true hole, or maybe with a pad which has an integral stud on top of it. But it is important that you consider how these mounting methods are impacting the connection stiffness, how they are impacting the measurement accuracy. You have to take those into account, and you have also to take into account how you will mount it really physically, if you have enough space to install the sensor, and also where your cable will be located. Don't forget that the cable is part of the measurement chain. So all these things must be taken into account when you're thinking about your measurement. Ground isolation is getting more and more interest because we have more and more measurement on electric machines in automotive, and basically ground loops can take place when you're measuring basically an object which has a different ground with respect to the data acquisition system. So at the end of the day, you're going to have a response which is polluted with peaks at 50 or 60 hertz and multiple of them that are difficult to eliminate. And here the shortcut is basically to consider an isolating pad, a sensor with embedded ground isolation, so with integral ground isolation, sensors which have particular materials like anodized aluminum on top of it, or possibly I would consider mounting the sensor in a region of the object where you already are sure that ground loops will not take place, like with isolating material, for example. So having said that, I would say that we went through the key parameters, so the key features that allow you to make most of your choice. With the ingredients, with the recipe I've given you so far, you would be able, I would say, to choose the sensor at least 90–95%. However, that's not the whole story, because I would suggest you to still have a look at the data sheet to see the type of products you have in your hand and how it might respond to certain testing condition. You might want to check that the housing material is suitable for the testing condition. You might want to choose whether you need a connector or an integral cable, whether you need TEDs or not, whether you might want to have a certain level of sealing of the housing, what is the transverse sensitivity, and so on. Of course, we are fully available and willing to support you when it comes to the choice of the sensor, of the accelerometers. And we suggest to also have a look at the product manual to have more details. It is an interesting and important resource, the product manual, which will answer many questions you might have. Good. Now let's have a look at section 2, key requirements and Keystruct products. Of course, automotive has thousands of applications where you might employ accelerometers. Here we are presenting them in 4 categories. We have engines and powertrains, vehicle dynamics and durability, electric motors and powertrains, and structural vibration and model analysis, which also includes, of course, general purpose vibration, troubleshooting, and so on. The first application I'm going to deal with is the engine and powertrains. Here, what is important in terms of G ranges is to be around 250, 500, 1000 G. These are very common G ranges for this type of application. Probably 500 is really the most common for engine applications. What is key is the thermal performance. Thermal performance is something on which powertrain NVH engineer cannot compromise on for obvious reasons. So thermal stability, a wide operating temperature range are important. Having a RAD design, resistance to harsh environment are also very important to consider when selecting the right accelerometer, because the sensor which is placed, for example, in an engine bay must withstand aggression maybe of oil, grease, dust, and so on. So it is important to take that into account. Space is also very limited, usually around powertrains and engines. So easy mounting might be something you want to take into account. Sensor which allows easy orientation, for example, or screwing in different directions could be important, as well as the positioning of the cables. So it is important for you to think what type of cables and how can the sensor be connected to the rest of the measurement chain when you're making the selection. And in these categories, of course, all applications like engines, engine components, hybrid engines, gearboxes, exhaust and radiator application, mounting points, and then, of course, motorsport applications. So let's say that whenever you are dealing with this type of testing applications, these key requirements might be a very good starting point for your selection. And when it comes to history products, we have an 8766, which is a very versatile sensor. It's we have it in various G ranges, 50, 250, 500 G, and more. It mounts a piezo star, so it's a rather, as you see, it's a rather small sensor. It mounts a piezo star, which means it has thermal excellence. It goes up to 165 degrees, and it has probably the best thermal stability on the market. It mounts three threaded holes which allow flexible mounting. You see them here, one on each side. So if you want to screw it in different directions, you can actually do that. And one thing is that with such a feature, we are also able to better calibrate the sensor, because we don't have to calculate the sensitivity from one axis where we actually have mounted the sensor on. Sensor is small, as you have seen, is light, and it has a hermetic titanium housing, which allows for the right ruggedness, which allow also to deal with engine applications. This sensor has TEDs up to 165 degrees, which of course boosts the efficiency of the test setup. We have 8765, which is a sensor which also mounts piezo star. So you see it here, also very small sensor. Mounts piezo star, which again guarantees rather high, rather broad temperature ranges and very good thermal stability. It has a through hole, which allows to easily orientate the cable when you want to screw it, and it ensures the right stiffness, very strong stiffness of the connection. It has a ground isolated integral pad, so you don't have to mount an additional pad to ground isolate it, and it has a low profile, which is very good for tight spaces. These two sensors are IEPs, tri-axle sensors. We also have single axis sensors, which are very used in the engine and powertrains area, like 8715, 8714. Both of these sensors have various ranges, but the first one is mounting piezo star, which ensures a better thermal performance. Although the second one, even though it's mounting a ceramic sensor, thanks to its design, it goes up to 165 degrees. So it still has a rather broad operating temperature range. Both of them have a through hole, which allows easy orientation of the cable. Of course, you can also glue it if you wish. And both of them have a ground isolated integral pad. One other differentiating feature between the two is that the 8715 goes up to 15,000 hertz in terms of frequency range, which makes it a very interesting choice when you want to push your frequency range. One last sensor I want to present is a charge sensor, 8248, which does not have electronics in there by definition. It has a through hole, so you can easily orientate the cable. It reaches 260 degrees because it has no electronics in there, and it is rather rugged. Let's say the right level of ruggedness you would need for engine applications. Vehicle dynamics and durability. Here, in terms of requirements, we move lower when it comes to G ranges, 2, 10, 50 Gs maximum. It is important to capture the response down to DC, so to 0 hertz. A low frequency content might be very relevant for this type of applications. And it is important to pick a sensor which has a rugged design and is resistant to harsh environments. Like you see in this picture, in these pictures, you see that often the sensor is placed outside the vehicle or maybe in the wheel region close to the brake. And here you have impact of basically even mud, rain, dust, whatever is outside the vehicle, and the sensor must withstand that. Typical application which respond to these requirements are battery excitation, road load data acquisition, chassis test on shakers, for example, drive comfort, ride quality, drivability, handling, motorsport. All these, I would say, require in general rather low frequency range, or most of the cases they do. And for these applications, the products that suit well. The requirements are the 8316, 8396. The first one is a single axis sensor. The second one is a triaxial sensor. Both of them are MEMS and share many different characteristics. Both of them have various ranges available, starting from 2G. They have 10G, 30G, 50G ranges, which are suitable for vehicle dynamics and durability. You, of course, by definition of MEMS technology, you will be able to reach low frequencies down to 0 Hertz. Both of them are ground isolated. I've got an 8396 here with me. You can see it. It has both an isolation pad here and a hole, threaded hole for mounting with a pad. So you can also create ground isolation with the pad and maybe glue it or screw it on the surface. Both of them are rather rugged, and they have a very interesting characteristics that there are some versions which allow to output the temperatures. So you can actually have also the temperature at which the sensor, so which is actually sensed by the sensor itself. It could be useful for correction of your measurement, for example. There is one last characteristic which I think is interesting, and is the possibility to set the output based on the options available at different configurations. You might have bipolar output, you might have differential output, or you might have unipolar output. And this could be very handy because it depends on which type of data acquisition you have, but also testing setup. For example, whenever you have disturbances due to electromagnetic field, differential output might be an ideal solution. Electric motors and powertrains, that's the next application. Here you see that the G ranges are slightly higher from what we have just seen. So 50, maximum 100 G, these are very common. Generally, the attention moves to the frequency range, which becomes interesting for obvious reasons. Electric machines show an interesting MBH at higher frequencies than traditional propulsion systems. It is important to have a rather low threshold, so being able to capture even low-level vibrations. Ground isolation is important for to avoid ground loops and ensure immunity to electrical, let's say to electrical influence you want to avoid. And of course, again, easy mounting, because you will have to deal with small spaces, so narrow spaces, like in the engine bay, for example. And there you want to have a sensor which allows to be easily orientated. Typical applications which respond to these requirements are those for electric motors, hybrid powertrains, also end-of-line testing, of which you see a nice picture here, and of which you see here how it was created, the isolation. So here the user did not use a pad, they used a component which is isolating the sensor from the stand. Compressors, power electronics, and charging electronics are also applications that might be covered by these requirements. And in terms of Kistler products, we have 8763. 8763 is again a sensor you see here. I'm showing it in the camera. This is a sensor which looks very, very similar to what I showed you before. Actually, it's almost identical. And it's a ceramic sensor. So it's not a piezo star sensor, it's a ceramic sensor. We have it also in various G ranges. And the nice thing of this sensor is that it can reach up to 15,000 Hertz in terms of frequency range. So you can go pretty high in frequency range with this small sensor. You have also 3 threaded holes, one on each side, which allows you to mount the sensor in various directions, so vertical or depending on how you want to align the axis. And it shares with the 8766 also the size, the weight, and the fact that it has a titanium housing. And nice thing is that as of 2021, we have improved the noise level of this sensor, improving them by at least 30%, which enables this sensor to be even more performant for applications like model analysis, and this we will see in a minute. So it's a pretty versatile and nice sensor. And we have again a sensor which is similar to what we have seen before, 8764. which is a sensor. I'm showing it again here. It's a sensor which mounts, again, a ceramic sensing element, not a piezo star like the case that you have seen before. So like the sensor you have seen before, 8765 it was. And also this sensor goes up to 15,000 hertz in terms of a frequency range. It has also a through hole, so you can easily orientate the cable and ensure maximum stiffness of the connection with the measured object. And it has an integral ground isolated pad to avoid ground loops, electrical ground loops. And because of the mixture of these characteristics, this sensor is preferred by a lot of our customers, which want to take measurements on electric motors or for electric mobility applications. We have again the 8766, which is ideal when you have some sort of dynamics in the temperature. We have seen this earlier. And the 8396, we have also seen this earlier. It's a MEMS sensors, but the fact that it provides a differential output, it also gives you the benefit of being good in situations where you expect a lot of electromagnetic fields around the sensor. Then we have the last application, structure, vibration, and model analysis. Very generic application as well, might be embedded into this section. Generally rather low G ranges, 5, 10, 50 Gs maximum. Low threshold, so being able to measure low vibration is important. Small size might be important, especially for light components and small mass. And of course, easy mounting. Typical application which responds to these requirements are component testing, FRF measurement, model analysis, operational model analysis, for example, full body or body in white analysis, and also general purpose troubleshooting. One thing about the mass, of course, when you're measuring, for example, here an oil sump, it makes sense to pick a small sensor. Otherwise, with the larger sensor, you're going to see the impact of these of the mass of the sensor and the response. But when it comes to a whole body in white of the car, then in this case, the presence of the sensor will probably not impact the response of the object in the frequency range you usually would be interested in. It is important to make this type of considerations when you're choosing sensors in these application areas. Products from Kistler's side, again, we have 8763, which I think with the updated electronics and lower noise levels is really providing you a sensor which becomes even more performant for this type structural vibration. So this type of application, structural vibration and model analysis. Going lower in G ranges, we have 8762, which is a little bit bigger sensor. It's a little bit heavier than 8763. We're talking about around 23 grams, but there's a rather low noise levels. It still preserves 3 holes, 1 on each side, and it is ground isolated. So it could be interesting in the cases where you might want to test a larger object like body in white. Then we have 8688 in case you want to reach lower G ranges, but you want to stay with a sensor which is compact in size, because this sensor allows, it's more or less the same dimension as the 8763, but still allows to reach 5G range and with a very low noise and various mounting options. Of course, Kistler also offer accessories. Main ones for this area are impulse hammer or impedance heads in case you want to use a shaker. And we have quite a variety of cables, of which I want to note a 1734. It's a cable that many of our customers love it because it's extremely flexible. You can actually deform it. You can even make a note out of it. Or not, you see, it's now it's all bended, but then it goes back to the normal shape without almost no deformation. So it has great flexibility, and it's extremely useful in the cases where you have complex geometries and you want to move your cable around and want to ensure that the cable is following such a complex geometry without preserving, so without keeping the deformation, this bend of more traditional cables. Good. Having said that, let's move to the third section, practical consideration. Here I'll try to give you some tips or some rules, let's say, how to optimize your test. And the first one is how to choose the location where to mount the sensor, because this is a question which sounds trivial, but it is not a trivial one, or at least I think it is not a trivial one at all, and it is very important to consider various factors. First thing to consider is how to use existing information to make decisions. So is there past experience that can guide you in the choice of the optimal location point, or are there results from simulation that can tell you where you should place the accelerometers, for example? Then another thing is, second point is to compare the sensor specs with the expected testing condition. And this is a point on which many times I find myself in the situation where the actual testing conditions were different from the expectations, and this caused damage into the sensor maybe, or the user was not able to measure what he wanted because there was a difference, a gap in between these two. Another suggestion is consider very carefully the mounting location. Is it accessible for mounting and dismounting? What type of surface you want to mount the accelerometer on? Is it flat? What type of material which type of material is it made? And is it smooth enough to allow to reach a certain frequency region, for example? These things you should ask yourself, as well as whether there is a possibility for ground loops that might at the end jeopardize the quality of your measurement. Think about the orientation of the sensor. Of course, after you have measured, you need to interpret what you've got there, and it is important to know where the axis is pointing to, especially if you want to validate a simulation, for example. You need to make sure that in the simulation, the axes are in the same direction as in the testing. And finally, I warmly advise you to think about the cable. How do you connect and fix the cable to preserve its integrity, especially when it comes to fatigue testing? Very often, the fatigue test is done not on the component itself, but on the cable, because maybe it was placed in the wrong manner, and at the end it broke down before the test could finish, and you basically lost the data and your time. So my suggestion is keep these points into consideration. And next session is about how to mount the sensors. Here I start with the stiffest mounting method, which is through an isolated stud, so through stud, which, as we have shown before, is the stiffest method. This can be done with a pad, with integral stud, or directly on the surface with a stud. And here it is important that you consider what type of surface the measured object has, whether it is smooth enough, whether it is flat enough, and it is kept clean. And it is important if you want to reach higher frequencies. So if you want to really exploit the stiffness you've created with the stud, keep into account putting some thin film of oil in between the surfaces to optimize that. Use proper tools like a calibrated torque wrench to avoid over torquing or under torquing. If you under torque, you will have a lower stiffness of the connection. If you're over torquing, the risk is that you're damaging your sensor or the surface on which you're applying it. Then when it comes to isolating pads, if they are already scratched, they might no longer insulate. And this is something you might want to consider. Have a look at them before you use them, and use the proper tools to remove the sensor at the end of the testing. This is important. Another mounting method is adhesive method, which could be done directly on the surface or via a pad. And here you can use wax, retro wax, for example, when the low acceleration is low, temperature is ambient temperature, near to ambient temperature. Otherwise, you might want to glue. Many customers ask us what type of glue can we use. Of course, if you have this type of questions, just let us know. Otherwise, you can also have a look at our material, the material we share on the website, and there you will find indications. And it's important there that you you use a thin layer of glue to maximize the stiffness of the connection. and really make sure at the end of the test you use a suitable debonding agent to remove the sensor, because these will make the dismounting much easier and safer for the sensor. Finally, we have magnetic base, which is the less stiff method for this for acceleration measurement. Of course, this method is very efficient because you can move the sensor position, so you can change the location very easily with little effort, if you accept the limited frequency range given by the magnetic base. One thing that I want to tell you is be careful when you are installing the sensor, when you are approaching the surface normally, because that can generate, so if you approach the surface normally, that would generate a shock that in certain cases might be dangerous for the integrity of the sensor. The right way of doing that is to approach the surface at an angle and then let the rest of the of the base lie on the surface that you want to measure, because that generates a smaller shock, so lower acceleration levels and lower risk of damaging your sensors. One last word I want to say is about cables. It is important to take them into account, as I told you during the, I told you already a couple of times, they are part of the measuring chain. You need to preserve the integrity during the test. To do that, the best thing is to minimize the free length vibration of the cable. You could ensure this by taping the cable rather close to the sensor, for example. This should minimize the free vibrating length of the cable. Make sure that you tape on the same object you're measuring. So if you see here in the picture on the right, if the tape is done on the side that is not moving, so not on the measuring object, this could create issues. So let's suppose that this is a shaker, this is the expander of the shaker, and is moving, while this is the shoulder of the shaker, which is not moving. So basically you would have that the cable is going through a test itself. So you're basically checking the durability of the cable itself, and this might lead you to unpleasant surprises at the end. One last thing I want to tell you is, when you are basically mounting the sensor, so connecting the sensor, pay always attention the way you do it, because you should approach the cable connector to the sensor and rotate the crown of the connector and not rotate the sensor. If you rotate the sensor, the risk is that you damage the pins inside the sensor connector. Pay attention to this, pay attention to this, because very often this is the case that the pins get damaged because of the wrong process for mounting, for connecting the cable and the sensor. Good, then we come to the wrap up. What we have seen together today is first of all some selection criteria. So my goal here was giving you an overview of the key parameters you should look at to make the choice for the right accelerometers. I try to condensate the very important features you should look at to make most of your choice. My suggestion is, once you've done that, once you identify the ideal candidate, just have a look at the other parameters to understand and to try to imagine how your sensors would behave in the environment of your test. I think this is something would allow you to understand better what type of results you should expect. Then we had a look at the key requirements for automotive applications and the matching Kistler product. I try to guide you a little bit to give you an idea of the type of requirements you should expect if you are performing a test in the main area of automotive, and what type of products Kistler can offer. And then finally, I try to give you some practical considerations when it comes to mounting and putting your sensor in service. So just to make the most out of your test. So having said that, I would invite you to get in touch with us whenever you have questions or you want to get some help to identify the right products to get the most out of your tests. And I take this chance to invite you to our booth, to our stand 2012 in all 20 at the Tire Testing Expo 2022. This will be in Hanover. If you're there in 2 weeks from now, just pass by to discuss with us accelerometers or in general tire testing or dynamic measurement. We'll be happy to meet you. So having said that, I thank you very much for your attention, and I would ask if there are questions.
Hey, thanks, Roberto. We do have some questions that have come in. I'll just go through them. The first question is, are there drawbacks in using piezo star instead of ceramic sensors?
No, not really. So it is simply a different type of sensing element that we are using when we are using piezo star, and the type of difference, so there are differences rather than drawbacks. The type of difference you would experience with the piezo star is in general a wider temperature range and a better thermal stability. So it's almost perfect. You have seen that, and this is the main difference, I would say.
Okay. Another one is, can you better explain what type of output can be configured for the capacitive sensors?
Of course. So if we go back to the slide, so basically, as you see here, I reported the type of output you can configure. So you might have you can have a bipolar output voltage, so oscillating voltage from positive to negative. You might have it unipolar, so always positive, for example, or differential. As I said, differential is very useful when you have some sort of electromagnetic fields, for example. The reason for that is simple, is because the plus signal and the minus signal is annihilating the effect of the noise, and then it's a very good way to shield against those type of, so to shield the signal, to preserve the signal from those type of influences. Yeah, and that's it.
Right. With regards to electric motor applications, what type of mounting method would you suggest?
Well, this is very much dependent on the type of frequency range you want to cover. In general, I would consider, so as we discussed, the best way is to screw the sensor. Probably with an 8764, you can screw the sensor directly on the surface, and you would have the isolating pad, which is integrated. If you can't screw it, you can still glue the sensor, and you still benefit from the integral ground isolating pad. Otherwise, you can use just a pad which is screwed to the sensor, like the 8763 that we have here. You can screw the pad to the sensor and glue it to the surface you want to measure. Yes, the alternative is, of course, you can try to look for surfaces of your measuring object which are already isolated, and then you can go with an 8763, which is directly glue on those to avoid ground loops.
All right. I think there's time for one or two more. Any other questions that are in here, we can respond directly to you, because I think we're running out of time. Is there any specific advantage in having smooth corners for the sensors like the 8763 or 8766?
So yes, so I'm showing them in the pictures here. Actually, these sensors have smoothed edges to optimize. So it's an optimal design to minimize the mass of the sensor. Plus, it is a way to optimize the usability of the sensor, because we've noted that a lot of damages are taking place at the corners of the sensors. And with this, we sort of make the dismounting and mounting process a little bit safer for the sensor itself. So these are the two reasons why the corners are smoothened.
All right. One last quick one. What is the maximum temperature that the silicone cable can withstand?
So silicon cable, again, this is very flexible cable that I have here. This is up to 200 degrees C. So it's generally, it can withstand temperatures as like other cables, and also from a mechanical perspective, the performance it can provide is fully comparable to the other common types of cables. So the main advantage the user has is really flexibility, and for the rest, there are not many things the user has to worry about with respect to standard cable.
So on behalf of Kistler, Roberto and I would like to thank you guys one last time, everyone, for joining. There's a few questions that we will respond to those individuals directly. At this point, I believe we're out of time. So thank you again for joining, and hope to hear from you soon.
Thank you very much. Have a good day.